Okay, good. According today is the 8th of December. Well, we have one more meeting. Hey, wait a minute. Yeah, that's right. I did. Labs 4 and 5 are due today. Okay, due before, let's put it before 11:59 p.m. Okay, I need you to turn in those labs today, so I have enough time to correct them for 11:59. And we started simple harmonic motion. Okay, so one more meeting Wednesday, and then we have a final exam. Final exam is a different schedule, okay? The partial exams are from 9:40 to 11:40. The final exam is start half an hour earlier, 9:10 to 11:10. 15. Oh, so notice that the final exam is 1 week from now, okay? 1 week from now, next week. Today is the 8th, the final exam is the 15th. So 7 days from now. And let's see what we can cover. Let's try to cover as much as we can. Here we go. More students coming in. LACCD, the college, LA Harbor, 25, fall 25. And we have those notes here. Move here to this side. And let's see where we stop in the notes. We started simple harmonic motion. Oh, yes. So what we did, let's put the date here. Insert page break 12/08/25 Monday. Last time we derived the equations for simple harmonic motion, SHM, which corresponds to an object, a point, to a point particle, right? Let's look with point particle of mass m attached to a spring having a spring constant k. Okay, and then what else did we do? We used the results for UCM, uniform circular motion, to obtain the equations for simple harmonic motion. Okay, then ideal spring, let's see, simple harmonic motion. Did I do the simple pendulum as well, or I just gave you the, let's see. Oh yeah, I did this simple pendulum as well. Okay. I did the simple pendulum as well. We did the following. We did the following. One, derived the equations for simple harmonic motion, which correspond to a point particle of mass m attached to a spring having a spring constant k. Use the results of UCM, uniform circular motion, to obtain the equations for simple harmonic motion. Two, derive the equation of motion, right? Equal, let's put here. The equations of motion for the simple pendulum. Which are slightly different from the SHM, simple pendulum. Let's put it using the approximation for the small angles. Okay. So the equations of motion for the simple pendulum is just an approximation to the real life, but it's a good approximation. And with this approximation showed us that the equations of motion, its equations of motion, right? Equations of motion are very similar to that of the SHM, okay? So now we will derive the equations of motion for the physical pendulum. I just gave you the final result for the physical pendulum, right? I didn't derive it. Okay, I didn't derive it. And it's a rather similar derivation. It's very similar. The derivation for the physical pendulum is very similar to that of the simple pendulum. But first you have to know what is the physical pendulum is all about, right? Difference between the simple pendulum and the physical pendulum. Okay? Simple pendulum is a point particle attached of mass m, right? Attached to a string, not spring, but string of negligible mass, right? Simple pendulum. One, simple pendulum. A point particle of mass m attached to a string of length L of negligible mass, right? Physical pendulum. A rigid body of mass m, moment of inertia I, moment of inertia I, suspended from a point of the rigid body at a distance L of the center of mass, okay? Center of mass. And we are going to get more students coming. Here you go. All syllabus lab illustrations right here. What I want: rotational motion, simple harmonic motion. I want a picture, a figure, so you can visualize, okay, how the physical pendulum, how different the physical pendulum compared to the simple pendulum, right? You go. Simple pendulum. Here you go. Point particle, right? And string of negligible mass, length L. And what about the physical pendulum? Here you go. That's how the physical pendulum looked like. A very generic physical pendulum. There is a rigid body. This rigid body has a center of mass, and center of mass is the point where the whole mass of the rigid body is supposed to be concentrated. I didn't elaborate on that, okay? But we don't need to elaborate, because the center of mass of the objects that we are going to treat here in this course are exactly the center, the geometrical center of the object, okay? In this case here, it's very difficult to find the geometrical center of this object because it's a generic rigid body. But if we are dealing, for instance, not with something like that, not with a generic object, but let's say a strip, right? Like this one. And I'm going to the center of mass of this object will be exactly at the geometrical center of this rectangle. Let's put it a rectangle, okay? And let's see, I am suspending it from, and I'm going to show exactly where the center of mass is. It's possible to calculate that too. There is a formula to calculate the center of mass of different objects. But for the sake of this course, we are going to be dealing with simple rigid bodies where their center of mass is located at the geometrical center. In this case, the geometrical center is right in here. Okay, center of mass. And the distance of the center of mass to the center of rotation like that. I want it. Here you go. Good. Now I'm gonna group it so it's easy to move around, right? I'm gonna take out this thing for now from here. And here you go. Now it's clear, right, that this rigid body is rotating at the very edge. That's the point of rotation. I am going to document yeah, Oh no, it's not what I want. Yo. Ungroup. Huh. Sometimes those things give me a hard time. Okay, good. Now I got it. Why he doesn't? Okay, good. Now he got it. And let's put a different background color here. Mm. More students coming. Let's get him. No fill. Black. Huh? And now there is a distance. I use the distance L prime of the center of mass to the point of rotation. And that's the L prime here. Okay. The rigid body, this strip, this rectangle has a mass capital M and moment of inertia I. Okay, that's a more specific rigid body. And then we have to look at the forces acting in this rigid body, right? But you know, that's a generic example. That's a more specific example. Okay, so let's continue with more generic example. We have to one important piece of information: the weight of a rigid body is applied exactly at the center of mass, at its center of mass. And that here is the weight that I'm going to, you go, weight. There's a free body diagram that I'm drawing here. And now we must also have a force being applied at this point, at the point of rotation. We also have a force, okay? It's not easy to find out what the direction of this force. So actually, the direction of this force changes as the object oscillates back and forth, okay? And, you know, I'm gonna put let's see. I'm gonna put a genetic force, you know, like that. No, I don't like that. Let's try a different one. And I want to put an arrow in this guy now. Format shape. Yeah, here you go. Let's see. No, this arrow is too small. Man, let's make it larger. What about now? Can we see the arrow? Yeah, now we can start to see the arrow. It's a genetic direction, okay? And that would be the normal force that that point is applying to the point of rotation of the rigid body. We don't have to know, and we don't have to know the exact direction, okay? And you're gonna see why. You're gonna see why is that. And just like before, just like we had for the point particle for the simple pendulum, we can get an equation of motion as well. Okay, that, what else can we get here? We can, this one. No, that's not the one I want. I think I want this one. Yeah. Yeah, here you go. I'm gonna need some grid lines. One, two. One, two. Like that. So I can get a good section of a circle right in here. Huh? That's the circle coincides with the center of the circle coincides with the point of rotation. There you go. And that's the angle. Let's see if you got it. Yeah, you got it. It's so small, this arrow. What's that, right? There you go. Now we got it. And then we can put the angle right in here, angle theta. Just like we did with the simple pendulum. We also use the angle theta with the simple pendulum, right? You go. Angle theta right here. And we are going to apply the equations of motion. We are going to apply the Newton's second law for a rigid body to find the equations of motion. Now I can erase my grid line. Let me copy that and put in the notes as well. It's snipping. It's snipping tool. Here you go. And here is a normal, N stands for a normal force, right? Normal force that the point of rotation is applying to the rigid body. Two forces, the weight and this normal force here that I put in the most genetic possible way. Physical pendulum, a rigid body of mass m, moment of inertia I, suspended from a point of the rigid body at distance L from the center of mass, right? You go see below. Like that. And now we are going to do exactly what we did for the simple pendulum. We're going to use Newton's second law for a rigid body. And I'm going to copy the whole thing here. It's not going to be exactly the same, but it's going to be very similar than what we did for the simple pendulum. Here you go. Net force, net torque applied to the rigid body. Net torque applied to the rigid body is the torque due to that normal force there at that point of rotation, plus the torque applied by the weight of the pendulum. We're taking the axis passing through the point of rotation. Consequently, the torque applied by this normal force is zero. Remember that I told you I don't need to know the value or the direction or even the direction of this force here, of this normal force. We don't have to know because its torque is zero. And what else? We gotta get the torque of the weight. The torque of the weight in this case is going to be this component that you see right in here of the weight, the theta component of the weight. The weight has a radial component from this point of rotation, and it has a tangential component with respect a theta component, right? Which is also tangential component of this weight. What else do we have to know? Okay, we know that this angle here must be theta as well, right? Let's go back here. I'm going to extend a line that's going to coincide with that distance L prime. Okay. Why am I doing that? I'm doing that just to prove to you that this angle theta is going to be equal to this other angle right in here, the angle that the weight makes with that dashed line. That's why I'm doing that. Okay. The weight has a component along this theta direction that is responsible for the torque. That's the component of the weight that's responsible for the torque, right? And then we have this other component here that does not contribute for the torque. Does not contribute for the torque. And I'll get this one here and place, oops. Right in here. Same angle. Okay, that's this one here. I'm gonna call the theta component of the weight. And I will subscript it. Font, right in here. Subscript. Okay. That's going to be the component of the weight that contributes to the torque. And this component of the weight is going to be the weight times sine of theta. Let's go back to our, okay, that's exactly what I have here. See that? mg, which is the weight sine of theta. But let's not forget too that, you know, we must multiply, instead of L prime, let's use L, okay? Let's use L instead of, that's the distance of the center of mass to the point of rotation. So, and that's what I have right here. Theta component of the weight. Let me put that second line, right? Theta component of the weight. Okay. Times L. And let me copy this one that has an updated version of the parameters, right? And I will over, here you go. Now I got it. The weight goes against the direction of measurement of the angle. That's why we have a negative sign here. Okay. And mg sine of, we're going to have the negative, right? The net torque must be equal to the moment of inertia times the angular acceleration. The moment of, I will keep it I here. We don't need that anymore, right? we don't need that either. Okay. Remember what you saw before was for the point particle, derivation of the point particle. Let me zoom in. View, zoom 200. Like that. And now, side by side, right? Put it side by side what we did there before. Let's see here. Now, what we're going to do, we're going to write alpha, the angular acceleration, in terms of the other parameters. And the other parameters are MGL. Let me copy twice. You go. MGL sine of theta divided by I. Right? And let's put it, we're going to make a table here so you can compare the derivation for the point particle. Simple pendulum, right? Let's put simple pendulum, physical pendulum. Side by side, how their derivation compares. We did for the simple pendulum, right? In both cases, we are going to have the net torque. Should go. Physical pendulum is right in here. Simple pendulum. Okay. Instead of N is going to be the tension, right? In both cases, we are going to have the net torque is going to be given only by the torque of the weight. Okay. We are going to have this one here. Mg sine of theta. But with a negative sign. On the other side, we're going to also have Mg sine of theta with a negative sign. In the next step, we use Newton's second law for a rigid body. Okay, exactly the same equation. The only difference applies here is that the moment of inertia of a point particle is going to be ml squared, right? Here I don't change anything because it's a generic rigid body. With a generic rigid body, I just call its moment of inertia equal to I. Because ml squared cancels out with ml on the left side. Go. ml. We end up just with L here. Here we do not have any simplification to do. Next. And now I'm going to isolate the alpha angle. the alpha acceleration, angular acceleration. And I'm going to do the same here. What changes is going to be this parameter that goes upstairs, MGL over I. And then we do exactly the same approximation. We do exactly the same approximation that we did before, right? So here we go. I'm going to use approximation sign right in here. This one. Sine of theta becomes theta. Sine of theta becomes theta. What changes is going to be this multiplicative factor here. Okay? And now we put all the equations side by side, and I already did that. There you go. I can erase that stuff here, right? Let's take a look. Here goes simple pendulum, and I'm gonna copy the whole table that you see here. Here you go, simple pendulum. Okay. What is the square root of G over L becomes the square root of MGL. I'm gonna put capital M here. Capital M, GL instead of LL prime, right? We're using that. Capital M, capital M. Let's erase L prime here. And square root of GL is replaced by square root of MGL divided by I. Position, velocity, linear acceleration. Let's see. Position, velocity, acceleration, not linear acceleration, but acceleration, right? Here is linear acceleration, here is linear acceleration, right? And here is angular acceleration, here is angular acceleration. So let's replace the table here instead of linear acceleration here. Just acceleration. The acceleration can be either the linear acceleration or it can be the angular acceleration. I will replace everything here to make it consistent with the notation. Okay. And now we can suppose that we have a rod of mass M, right? And length 2L. Let's put here rectangular, here you go, rectangular strip of mass M and length 2L. With the longest, length 2L, let's put it this way. So what we have to do, we have to go back to the book and find out what is the moment of inertia for this regular strip, rectangular strip, right? And then we can also rod of mass M and length 12, right? And then we can also write down, let's see, ring of mass M. Let's see, rectangular strip of mass M and length 12. And let's see, one more thing that I've got to tell you. Suspended from its edge, right? Rod of mass length 12 and suspended from its edge as well. and suspended from the edge as well. Okay, so you just have to apply the I for all those cases here, and then you get the right equation of motion, right? Let's see if I have moment of inertia for those. Let's see. Moment of inertia for those cases. If you don't have it here, we have to look there in the book. Doesn't look like we have it here. Let's go to the book. Wide plus. Quick access, login to wide plus. Taking time. Huh. Let's try to get login. Thinking. Wow, internet is slow today, huh? Well, let's look at the let's look at the internet, right? Moment of inertia. Moment of inertia of different solids. Yeah, we have it here. Let's see. This one that I want. Something like that is in your book, but why is so difficult to see? Let's see.
Como vai a vida de casal?
What's that?
A gente quer bem. Vai bem.
That's not
Nossa,
what I
tão
want.
mal assim.
That's not what I want. Let's see if we can. Let's see. Let's look at this one here. Yeah. Here you go. Hoop or ring, right? If it's a ring, the moment of inertia through its center is mr squared. However, that is very, very important. Let's see if they have it here. It doesn't look. Oh yeah, it does have. Okay, that's the one we want. We want the axis. Let's see. I want the axis passing through the edge of the ring. Okay, the axis passing through the edge of the ring. It doesn't have it here, but I'm gonna tell you what it is. Mr squared, right? Plus mr squared as well is the, for a rigid body that looks like just like a. Let's look at the rod first. Let's see here. Okay, this one here. Okay, for the rod first, I is ml squared over 3. Okay, passing from the edge of the rod. Rectangular strip rod. Okay, I equal 1/3 ml, but it's going to be 2L in this case, because I said that the rod is going to be 2L, right? 1/3 like that. So this I must be replaced like here for the rod. Now, what about the other one? Here you go. A rectangular strip. Okay, and now my axis, it doesn't have here, is the axis that passes through the edge, right here. Okay, and my rectangular strip, 2L length. Okay, and has a width 8. It's gonna be what? MA squared plus B squared. And because the axis is at the edge right in here, is a distance L. right? You have to sum another ml squared. L, in this case, L would be B over 2, okay? So let's write it down. Rectangular strip, I. Those values for the moment of inertia I'll give to you in the exam, okay? Let's see, someone's trying to come in. Okay. I would be Emma. I'm going to write down just like we have there in that B square. Right here. Divided by 12. But that is the moment of inertia going through the center of mass. If you want to an axis that passes through the edge of the object, then you have to sum, okay, times a distance of the center of mass through the edge. Okay. That in this case would be B over 2, okay? Instead of length, let's see, gonna be length 12. So we have to put 2L right in here. And we have to put 2L right in here. Okay? And then we get of length 2L with A and suspended from its edge. Here's gonna be 4L squared. Here is going to be 2 cancel out with 2, right? And we end up with L squared. You got to do the math. I'm not going to do the math, okay? But you can see that we can simplify this term here with this other term here, okay? That's the rod and the ring, right? Suspended from its edge. Let's do this other one here. I need to close this one. Here you go. The hoop or the ring. The axis passing through the center, but we want now this axis at the edge of the hoop, at the edge of the ring. And then what would that be? Would be, that's what's called I'm gonna put it the genetic formula, okay? The ICM, okay, plus M D squared. That's what I did right in here. And then what I'm doing also for the ring, right? The moment of inertia going mr square, okay? Let's see, not length, radius of mass m, radius r, and suspended from its edge. Okay, the distance d from the center of mass is going to be r squared. And then we get 2mr squared. Okay, so those are the specific examples for different rigid bodies, different geometries of the rigid body. Here is the genetic formula that I wrote down in terms of I, right? And that's how it looks like. Let's take a look at the, okay, right here. So here you go. section 10.5 through 10.8, we will skip. And then we finish simple harmonic motion. We finish simple harmonic motion, and what time is that? 10:32, right? Let's move a little bit. Let's go lecture another 20 minutes, and then we have our break. SHM, simple harmonic motion. Okay, and now we are going to do chapter 11. Chapter 11, we're going to be skipping some of the material in chapter 11. Okay, mass density, or just density, okay? Or just density. Pressure and depth in a static fluid, and then we have Archimedes principle. We're going to cover all those four sections here. We're skipping some of the sections there. Let's see if the book opened up. Oh yeah, here you go. Finally, took a long time. Huh? Physics, right in here. Wow, Wiley is so slow today. Let's see this one here. Launch. Okay, that's this section here. Chapter 10. Okay, we are not doing damped harmonic motion. We are not doing driven harmonic motion. We're not doing elastic deformation. We're not doing stress strain Hooke's law, okay? And the pendulum. Let's take a look at the pendulum here. Yeah, that's a simple pendulum, right? Let's see if he did the that's a simple pendulum. Let's see if he did the physical pendulum. Yeah, it doesn't look like he did the simple pendulum, right? He did a simple pendulum, but not the physical pendulum. The next one is on fluids. Here you go. Mass density, pressure and depth of a static fluid. We're skipping this one here, pressure gauges, devices that can measure pressure, okay? We're skipping Pascal principle, but we're doing Archimedes principle. And we're skipping everything else. Okay, it would be too much for this course. So cover everything else here would be too much for this course. And this one is a rather simple chapter, okay? Density or mass density. Or mass density is the amount. There are other types of density out there. That's why he's being specific about mass density. But mass density we usually refer to as being density, okay? Like I said, there are mass, in addition to mass density, there are other types of densities as well, like in charge density, electric charge density, okay? We have that. But if I don't specify what type of density it is, that's because I am referring to mass density. Amount of matter per unit of volume. Okay, 1 cubic centimeter of water and 1 cubic centimeter of gold, right? Compare, for instance, 1 cubic centimeter of water, a volume of 1 cubic centimeter, and 1 cubic centimeter of gold. Or let's say 1 cubic meter of water and 1 cubic meter of gold. The mass of gold will be larger because gold is denser than water. Okay, and what's the definition? What's the mathematical definition of we used this concept of density in our very first lab. Do you remember? And we're in the very first lab, we're working with the spheres, right? And the density, mass density is what? Mass of the object divided by the volume. The unit of measurement is the unit of mass divided by the unit of volume. And there are tables out there that document the densities of different materials, of different substances. And let's not forget the SI unit for density is the kilogram per cubic meter, but we also use other types of units as well, like the gram per cubic centimeter, right? And whatever, and others. For the case of the density of the water is the standard, is the reference for every other density. The density of the water is 1 gram per cubic centimeter. And we can translate that in kilograms per cubic meter, okay? We can do that. How do we do that? You just write, the grams in terms of kilograms. And what 1 gram is about? 1 gram is 10 to minus 3 kilograms, right? And what one centimeter is in terms of the meter is 10 to minus 2 meters, like that. And now you just substitute those two relations to obtain the density of the water in terms of kilogram per cubic meter. Here you go. 1 gram is substituted right in here. 1 centimeter is substituted right here, but don't forget that what you have right in here, okay, what you have right in here is a parenthesis, right? What you have right in here is a parenthesis. Here you go. It's like that. And because this is a parenthesis, let's go to the next step. We must replace this expression right in here in 1 centimeter. So everything within the parenthesis is raised to the cube. We didn't have this problem for the gram because the gram is raised to the first power, right? We keep on, go ahead. Let's keep on deriving 10 to minus 3 raised to the cube. Raised to the cube, like that. And kilogram raised to the cube, like that. See, the 10 to minus 3 must be raised to the cube as well. Otherwise, you won't get the right solution, right? Minus 3, 10 to minus 3 raised to the cube is 10 to minus 9. And now I can take my 10 to minus 9 outside the parentheses. And, oh, it's not kilogram, right? It's meter. Here you go. It's meter. Let's correct that. Meter here, meter here, meter here. Another meter here. Another meter here. And then we'll finally get what? I can invert the powers, right? Negative power downstairs, go to the upstairs, and then you change the sign and you do the same for the other. So now I'm going to emphasize that those powers became positive. Oh, I made a mistake here, right? Here, another mistake. Nobody called me out on that, right? It's not 10 to minus 3. 1 centimeter is 10 to minus 2. Okay, so that's why the numbers were not matching what I was thinking it was supposed to be, right? 10 to minus 2 becomes 10 to minus 6. And then instead of 10 to plus 9, becomes 10 to plus 6. Okay, now we got it right. And a million divided by 1,000 is 1,000, right? And this one disappeared. So 1 gram per cubic centimeter is in reality 1,000 kilograms per cubic meter, changing from one unit to the other. Okay, changing from one unit to the other. Let's correct that here. Good. And here's a table of densities. You don't have to memorize this table, but you have at least you have to know the density of the water. 1 gram per cubic centimeter. That's not difficult to memorize that, right? 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. Let's take a look at the densities, the mass densities of different substances. You go, larger. Table of densities. Platinum solids, right? 21.4. Gold, 19.3. Uranium, 19. Lead, 11.3. Okay. Plastics. Plastics, the type of depending on the type of plastic, is going to have a lower density compared to the water. Ice, 0.92. Ice, and we're talking about ice at 0 degrees C, okay? Notice that ice is 0.92, is lighter than liquid water. Liquid water is 1 gram per cubic centimeter, right? And that's why ice floats on water. Solid water floats on liquid water. That's because its density is lower than that of water. Okay, mercury, liquid mercury has a very high density. Carbon tetrachloride, saturated salt water with lots of salt in there. 1.2, very heavy. Heavy because of this salt. Water, 1.00. If you cool down the air to minus 193 degrees C, air becomes a liquid with a density equal to just slightly below the density of water, 0.887. Methanol, oils, gases, air. Here you go. Here's the density of air. Air at atmospheric pressure and normal temperature and ambient temperature. The one that you have to memorize again is this one here. Just one you have to memorize. Just one you have to memorize. The one of water. 1 gram per cubic centimeter. Okay, so we are done with mass density. Let's get there. We're done with mass density. Most likely you have seen that in chemistry, right? The next topic is going to be pressure. Let's talk about pressure. Let's see if we can do that in the next 3 minutes. So we finish pressure and then we go on the brake. Okay? It's a very important concept of pressure. Okay, and there is a definition for pressure. Can you remember that? Memorize that? You know, the pressure is a type of force. Okay? It's a force that you apply it over a given area. Okay, if you have, for instance, 10 kilogram block with 1 square meter applied to a surface, and I'm going to illustrate that. Here you go. Idea of pressure is a very important concept one. Here you go. Consider a block. Here you go, like this one, 1 square meter, mass 10 kilograms. This block is applying a force in this surface here equal to 100 newtons. 10 kilograms times G, right? And the pressure, how is the pressure defined? Is going to be the force divided by the contact area. In this specific case, is 100 newtons per meter squared, okay? Or 100 Pascal. That's the unit for, that's the SI unit for pressure, the Pascal. Okay? Depends on the contact area, okay? It's the contact area here. So because the pressure depends on the contact area, if I reorient this block to be upright, you know, the pressure is going to change. The mass is not going to change. The mass is going to be the same. The weight is going to be the same, right? Depends not only the mass, but also the area, but also its contact area. Its contact area. So again, if I orient my block, here you go. Like that. 350. Now the contact area decreased by half. The contact area decreased by half. Consequently, the pressure increased by twice. Okay? So now we can, that's the idea of pressure. Let's go for a break. Break from 10:50, right? 10:50 a.m. to 11:05 a.m. Any questions? Yeah. Okay, if there's no questions, let's go for our break and we'll be back in 15 minutes. Okay. I'm back here. Let's go and share the screen. Okay, that's what we had before, okay? So can you remember this definition? Okay, force divided by the contact area. So we have two different examples of how this concept works, right? We have a block that has the largest area of contact over the surface, is one pressure. And then if we reorient the block, put it upright, the pressure increases. Here, this area would be one square meter. This other area here would be half a square meter, right? It's not necessarily in let's see, the drawing is not necessarily a realistic one, okay? But at least you have an idea of how this concept works. And here you go. Does it make sense? Okay. So the smaller the area for the same force, the higher the pressure. And also the smaller the force for the same contact area, the lower the pressure, right? Goes like that. The pressure is directly proportional to the force, inversely proportional to the area. Just recall that it's far more painful for you to stand on the tip of your toes, right? Than to lay down on your side, front or back. Let's see. It's far more to stand on the tip of your toes than to stand on your whole foot, right? Why is that? Because the pressure is larger for the first case. Okay, is the pressure is the measure of a concentration of concentration of a force. That's what it is. Is a measure of the concentration of a given force. And another way I like to define pressure, right? Pressure is like a force density, but this density is not a volumetric density, but it is a area density. It's a density in terms of the area. This idea of pressure is a concept that is not restricted. The idea of pressure, let's write it down. The idea of pressure is a concept, okay, that's not just restricted to solid objects. Solid object in contact with a surface, but also to liquid and gaseous and gases. To liquid and gases, okay? And to liquid and gases as well. And we're going to do an example like that. Example, for instance, okay? If you are submerged in a body of water, okay? We feel a higher pressure than if we were above water. Okay, that's because the water above you has some weight that acts upon you. Also, consider that we are all consider that at this moment we are all submerged in an ocean of air, right? And this ocean is a mixture of oxygen, nitrogen, and traces of other gases. Okay? Oxygen, a mixture, and traces of other gases. So all these gases all these individual molecules have a mass and a weight. For this reason, they exert a pressure on all of us. Can you picture that? Okay. That's how we can quantify the pressure that we feel not only here at the surface of the earth, but if we are submerged in a body of water. In the case of this, the atmosphere, right, in this ocean of air, let's see if I have a drawing here. I'm going to illustrate that for you. It's better if we do an illustration so you can have a picture. Let's see, right in here. Fluids, right? So here you go. You saw this picture here. You saw this picture here, right? Pressure due to a fluid. And then here you go. Here's another picture that I want you to keep in mind. We are the surface of the earth. Let's see if I can zoom in. Zoom in. Blah, blah, blah. Zoom. We are the surface of the earth. Okay. And we have this huge ocean of air on the top of us. Let's say the atmosphere extended up to this height, right? Above a certain height, the air becomes very rarefied. And we can say that there's no atmosphere at all. We say that atmosphere ends at 100 kilometers high. So we have all this column of air exerting a weight over us. And this weight exerts a pressure. The weight of this atmosphere exerts a pressure. Here you go. So try to visualize that we are all subjected to a column of these gases that extend to approximately 100 kilometers high. All these gases, although they are very light, they do exert a force on us. But there are so many of those gases, right? But there is so much of there are so many of these molecules that the force they exert is not is measurable. Okay, it's measurable. Let's put it this way. However, there's an important difference between this type of pressure and the pressure that a physical object makes on a surface. Okay, however, there's an important difference how gases and liquids exert pressure on an object compared to the pressure exerted by solids. Okay, the pressure by a fluid is not just downwards in the vertical direction. It's not downwards, comma, in the vertical direction, but also sideways. The pressure exerted by fluids, the pressure exerted by fluids on an object will always be normal to the surface, whether it is along the vertical direction or horizontal direction. Okay, and we can come up with a very interesting example of how to calculate the pressure exerted by a column of water of height h. Okay, using this concept, this model, not this concept, but this model, right? Using this model of pressure, we can now determine the pressure that a given column of water and even air, okay, and even air exerts on you. as you dive deeper and deeper underwater. Okay. A column of water or any fluid. Let's put it this way, or any fluid. Okay. So let me give you an example. There's a very interesting example here. Find the pressure of a column of water of height h. Okay. And let's get that illustration. Here we go. This one here. I want to show this one here. Okay, consider a container. I'm gonna fill this container with a fluid. Let's start with water, right? The fluid being water. Let's not forget that there is this column of air on the top of on the interface between the water and air, and this column of air exerts a pressure. Okay, and I'm going to give you a numeric value for this pressure. Okay, at the surface, at mean sea level, the pressure, the air pressure is said to be 1 atmospheric pressure, 1 atm, which is another unit. Okay. And this unit, let's take a look here, is approximately 101,000 Pascal. Let's make sure that's the right one. 1 atm in Pascal, right? Yeah, 101,000 Pascal. There's a little bit more here, 101,325 Pascal. Okay, so 325 Pascal. PA. You abbreviate that by PA, which is Newton per meter square. Pascal is Newton per meter square, okay? Can you remember that? Just remember 1 atm, okay? And then it's fine if you say that 1 atm is 100,000 Pascal. I'm gonna put it approximately, right? Approximately 100,000 Pascal. It's much easier to remember that, right? 100,000 Pascal. So that's what the pressure, let me close this one here. Yeah, so that's the pressure that this ocean of air exerts on us here at the mean sea level. As we climb higher and higher, we're going to, this column of air is going to become shorter and shorter, and the pressure decreases, right? Let's write it down. As we climb higher, higher and higher, the length of the column of our air becomes shorter and shorter. For this reason, the weight of this column decreases. Consequently, the pressure decreases as well at the top of a mountain, right? Well, the same thing applies when we go submerged underwater, when you go underwater, okay? And we can calculate what's going to be the pressure of a column of water of height h. It's possible to do this calculation. Let's take a look here. Going back here to my drawing, that's how I represent the pressure at the surface of this water, that's mean sea level, a height of mean sea level. 1 atmosphere is approximately 100,000 Pascal, 100,000 newtons per meter square, right? Kilonewtons per meter square or kilopascal. But what about as we dive deeper in this tank of water? Here you go. I want to know what's going to be the pressure here at this depth, at the depth H. So we have this column of water waiting on us, exerting a pressure on us, okay? Next. No, you can model this column of water as exactly as a cylinder. As a cylinder of a given area A. Okay? So the first step is to state that the pressure due to this column of water, here you go, let's solution, is the force that this column of water exerts on you divided by the area. Okay? And this force can be written down as being equal to the weight of this column of water. You're going to see that this relation is going to give a very interesting final result. Okay? When we start solving problems like that, we start thinking, I didn't, for instance, I didn't tell you what's this area, right? If I don't know the area, what would be the mass either? We do not know what the mass is either. But oftentimes when we do this type of derivation, things that we do not know, they end up canceling each other in the derivation. And you're going to see it's going to happen exactly in this derivation, something like that is going to happen exactly like that. Oh, remember that the mass of an object, right, can be written down as its density times its volume, right? Density is mass over volume. Consequently, mass is equal to density times volume, right? Let's write that down here. Density, recall that density is mass over volume. Consequently, mass can be written down as being density times volume. Like that. When we replaced mass there in the equation for the pressure, we have something like that. But then there is one more thing that we can do. This volume can be written down in terms of going back to the drawing, right? Let's take a look here at the drawing. This is a cylinder, right? The volume of the cylinder is going to be equal to this area here that we do not know what it is, times the H, times the depth, which we do know. Okay, so here you go. Area times the H. Now, do we see what happens to the area here? It cancels out. We know G, the pressure is going to be a function of the depth, and it's going to be a function of the density of the fluid as well. If it's water, right, it's going to be 1,000 kilograms per cubic meter. So let's go another step. A cancel out with A. And rho Hg, that's what we get. Let's go further down. Let's elaborate a little more. If you are dealing with water, if the fluid is water, then the water density is 1,000 kilograms per cubic meter, right? Like that. Kilograms per cubic meter. And let's not forget that g is the acceleration of gravity. I'm going to make it equal to 10 meters per second squared, just to make our calculations easier, right? So here we go. Oops, not this one here. And what else can I do? I can put here, write that as being 10,000 kilograms. Meter here cancel out with this meter. And we end up with a second square downstairs, canceling out. Yep, 10,000 kilograms times h. H is also in meters. Okay. Let's write it down in terms of something else here. Now, what I'm going to do, I'm going to multiply by meter, and if, oh, not like that. I want like that. Multiply by meter and divide by meter, right? And then what I'm going to do, I'm going to cancel this meter with this other one. When I cancel this meter with the other one, we get, let's see here. I'm not going to cancel, sorry. I'm going to pass the second square to this side, okay? And now I'm going to, move this h over meter right here. There's a reason why I am dividing by meter. I'm dividing it by meter because I want to cancel the unit that's implicit right here in the h, okay? And now take a look. Kilograms are going to be even more obvious now. Here you go. I'm going to be even more obvious than that. Oh. Kilograms meter per second square is Newton, right? So let's write that down. Newton right in here and erase the meter per second square. Now, even better, I'm going to do better than that. Here you go. Kilogram. I'm going to put this meter per second square upstairs right in here. I'm not going to cancel. I don't want to cancel this meter here. I want to keep it this way. Kilogram meter per second square is Newton, right? And Newton per meter square is what? This is Pascal. Okay. 10,000 Pascal times the depth divided by the unit meter. I'm going to put it 10 to the fourth power. Okay. Notice that for every 10 meters of depth, the pressure increases by approximately 1 atmosphere. Did you say? Did you notice that? Right? H equal to 10 meters. Isn't that nice? The pressure ends up being equal to 1 atmosphere, right? 10 meters. Meter cancel out with the meter. And we get 10 to the 5th Pascal, which is one approximately, right? 1 atmosphere. Let me put that in approximation here. It's just 1% difference, a little bit more than 1%, almost nothing, okay? So for every 10 meters that we dive below water, the atmosphere, the pressure increases by 1 atmosphere. So for every 10 meters we dive below water, the pressure increases by approximately 1 atmosphere. Okay? Hey, but there's more. There's more. Here is the this pressure is the pressure due only to the weight of the water. Okay? If we consider the pressure, the air pressure above the water, we have 2 atmospheres, okay? 2 atmospheres. So it's gonna be like that. The actual, right? The net pressure should be 1 atmosphere that I'm gonna call P0 plus that equation that you got right in here. That equation that you got right in here. Right? H. Simple enough? Okay, so if you dive 10 meters below water, the net pressure is 2 atm. So if you dive 10 meters below water, the net pressure is 2 atm. If you dive 20 meters below water, the net pressure is 3 atmospheres, and so on, right? And so on. If you dive 30 meters below water, the net pressure is 4 atmosphere, and so on. And now, so if you are taking Physics 7, okay? If you're taking Physics 7 next semester, if you have to take Physics 7 next semester, I want to encourage you to register for my course. You know, I'm running out of space there for my course. For this course, which I'm going to teach, okay? To teach as well during the spring 2025. 25 though, 26, right? Physics 7 is a far more interesting course, but it's more difficult too. And it involves the physics of the 19th and 20th centuries, okay? At this point in time, I think I have already like 30 students, so we're running out of space. If you haven't registered for this course yet, I encourage you to register as soon as possible. Here's what we covered so far in this chapter 11. Mass density, pressure and depth in a static fluid. Don't forget, this derivation that we did was for a static fluid only. Static fluid, a fluid that's not moving, okay? The derivation that we did for pressure is for a static fluid only, a fluid that is at rest. Okay? If the wind is blowing, for instance, or if you have a water current, the pressure increases a little bit more. It's just like the wind in your hand, right? If I, right now, my hand feels a given pressure, but if I blow air in my hand, I feel an additional force. I feel an additional pressure due to the motion of the air. Air in motion adds to the pressure. And there's a way to calculate that, but we're not going to get into that, okay? We're not going to get into that. That's what we call ram pressure, okay? A fluid that's moving adds to this static pressure, which is also called ram pressure. Okay? Let's take a look here at the internet. Ram pressure. Ram pressure. What is ram pressure, right? Ram pressure is the force exerted on an object moving through a fluid. Okay? The relative motion of the fluid with respect to the object. If the object is moving through a static fluid, it still feels a ram pressure. But you can have the other way around. The object can be at rest with respect to the ground, right? And the fluid can be moving through it. So we're talking about relative motion. Or gas, right? Fluid or gas caused by the fluid being rammed into the object. That's what ram pressure is all about. We don't need to elaborate more on that. Okay, there is a way to calculate this ram pressure, but we are not going to get into that. We are not going to get into that. Okay, so just remember that pressure increases with depth, right? Now, because of this increase in depth, there will be a pressure differential between the top of an object and the bottom of an object. Can you picture that? Okay, so here you go. Here's my object underwater. Here's another object underwater. This object is subjected to this atmospheric pressure at the top, right? But it's also subjected to the water pressure, added to the atmospheric pressure. At this height here, the pressure is going to be the same. Notice that the arrows have the same length, right? To emphasize the fact that the pressure is the same. But on the sides of the object, we are going to have also a pressure that's going to increase. And there will be a pressure differential between this level and this other level. Furthermore, remember that I told you pressure is always something that is perpendicular normal to the surface, right? So if in the left side I have pressure from the left, on the right side I'm going to have pressure from the right as well. And at the bottom I'm going to have a pressure as well that's going to partially cancel the pressure that's coming downwards. So notice that since the pressure here is larger than the pressure here, there will be a pressure difference, an upward pressure differential. Okay? This pressure sideways, it cancels out. But not in the vertical direction. In the vertical direction, we are going to have this net pressure, which is going to result in a net force, a net upward force due to the pressure itself. This pressure, this force, we call it buoyant force. Let's write it down. Okay. Since the pressure, I'm going to write what I wrote before, right? The pressure at the bottom of an object is greater than the pressure at the top. The pressure, the upward pressure, right? Upward pressure at the bottom of an object is greater than the downward pressure at the top of this object, comma, there will be a net upward force, the light pressure, applied to this object. A net upward force applied to this object due to this pressure differential. Okay? This netward force is called, there's a name for this force, buoyant force, buoyant force, okay? And represented by the letter B. And the question is, how can we quantify this buoyant force? There is a way to quantify this buoyant force. And that's the reason we feel lighter underwater. Okay? That's the reason we feel lighter underwater. Because of this buoyant force applied on us. How is this buoyant force quantified? Well, this buoyant force is quantified by a principle discovered by Archimedes, one of the greatest geniuses in the history of mankind. Okay, even today we have been discovering stuff that he discovered at that time that we didn't know about him. He has this massive amount of work that he documented in his journals. Every now and then we discover some new information that we didn't know at the time. So here you go. Archimedes discovered the following. When you submerge an object completely underwater, right? This object displays its own volume of water, right? Why is that? This is because two objects cannot be collocated simultaneously, right? Water cannot be collocated with that volume that the object is occupying underwater. The idea goes like that. Here you go. Here's the volume of the object. The object is outside the water. When I notice that, here you go. I'm going to do like that. Right? Notice that before I submerge the object, the water is at a given level. But when I submerge the object, the water is displaced upwards. The water is displaced upward because this object is taking some of the volume that was originally filled by the water itself. The object cannot be collocated with the water that was occupying this volume here. So that's why the volume, that volume of the water must be displaced upwards. So you have to understand that, right? When you subject an object completely, this object displays its own volume of water. Remember that. volume V of water that has been displaced. What Archimedes concluded, right? What Archimedes found out is that this buoyant force that you have right in here, I'm gonna erase this one, buoyant force, buoyant force. What Archimedes discovered is that this buoyant force is equal to the weight of the displaced water. That's something that Archimedes discovered at that time. At that time it was considered a law, okay? But today we can derive it mathematically. So what Archimedes concluded his time was the following. The buoyant force is equal to the weight of the volume of the displaced fluid. Okay? So let's come up with a example. Oh, it's already 11:50, right? Let's take a break before we do an example. So break 11:50 a.m. to 12:05 p.m. Okay, next we will after the break, right? After the break, we will look at an example that deals with the buoyant force. Okay. So from 11:50 to 12:05, I see you in 15 minutes. And now that we know how to calculate the buoyant force, right? The buoyant force is just the weight of the volume of the displaced fluid. The weight of the buoyant force is equal to the weight of the volume of the displaced fluid. That is displaced, weight of the volume that is displaced by the fluid, like that. So let's go ahead and example. Okay. Consider 1 cubic meter of water, of displaced water, right? Displaced water. What is the buoyant force of this displaced fluid? Okay, and then you write down solution. So just go back and consult Archimedes' principle. The buoyant force of the displaced fluid is equal to the weight of the volume of this displaced fluid, right? The buoyant force must be equal to the weight of the displaced fluid. Since 1 cubic meter of the fluid was displaced, comma, then its buoyant force must be equal to the weight of 1 cubic cubic meter of water, right? So let's first we calculate what is the mass of this 1 cubic meter of water, and then we calculate its weight, right? So let's go back to, and in order to calculate the mass, we go back to the equation of the density that we got before. Right in here, this one, right in here. Oh, even better, this one here, okay? This one's already converted. Mass of the displaced fluid is going to be equal to the density of the water times its volume. The density of water we already calculated, how much that is 1,000 cubic meter. Okay. And the volume, no, wait a minute. Not 1,000 cubic meter, it's 1,000 kilogram per cubic meter. Right? And the volume, we already said that is 1 cubic meter. So that's going to be the mass. Meter, cubic meter cancel out with cubic meter. I will cancel this one here. So we are left with 1,000 kilograms. Okay. And now the weight is given by mg. Okay, and weight is mg. M is 1,000. Let's see, 1,000 kilograms. And g is 10 meters per second square. So what we get? We get 10,000 newtons. 10,000 kilograms per 10,000 kilograms meter per second square, or 10,000 newtons. That's going to be the buoyant force if we were to displace 1 cubic meter of water. Okay, so let's write that down here. Consider if we displace, let's write that. Let's reformulate this problem. If you displace 1 cubic meter of water, right? Comma, what is its respective buoyant force? What is, okay, like that. It's better. Formulated in a clear way, right? Now, 10,000 newtons. And then next, there are other things that we can do about that. You know, it's what we're going to do now is to find out what are the conditions for an object to float, sink, and remain at the same depth. Okay. There are 3 important conditions. Submerged, here you go. Submerged objects can either sink, float, or remain neutrally buoyant. Just like fish, right? Just like a fish. And neutrally buoyant, I mean, at the same depth, completely submerged, but at the same depth. Completely submerged, but at the same depth, just like fish. Use Archimedes' principle. find out the conditions of the density of the object with respect to the density of the fluid for the object to 1, sink, float above the water, and 3, remain completely submerged but under neutral buoyancy. Buoyancy. Okay, like that. Submerged object can either sink, float, or be neutrally buoyant. What neutrally buoyant means? Neutrally buoyant means when an object is completely submerged, but it's at the same depth. Just like fish, right? Just like a fish. So the next one, use Archimedes' principle to find out the conditions of the density of the object with respect to the density of the fluid for the object, for the following condition, right? For the object to sink, to float above the water, and to remain completely submerged, but under neutral buoyancy. And what we have to do, we have to look at the forces acting in an object, okay? In the submerged object. This one gonna be here, you know? Remember that an object that's completely submerged, you know, experience a buoyant force. But in addition to the buoyant force, it also is subjected to its own weight, right? That's all the forces. And by the way, Higo, I'm gonna do something else too that I have to tell you. Neglecting the force of resistance of the fluid, okay? The force of resistance of the fluid, comma, very important. So since I'm neglecting the force of resistance of the fluid, so we're going to have only those two forces, the weight and the buoyant force. If the object is sinking, it's because that its weight must be greater than the buoyant force, right? So let's see. Sinking object. Let's write down here, solution. Sinking object. Weight must be greater than the buoyant force. Okay, so let's put it here. You know, the weight of the object, which is mg, must be greater than the buoyant force. Okay, like that. That's how you write. Okay, that's the condition for an object to sink. And now we are going to write down the buoyant force here. The buoyant force is going to be equal to the mass of the displaced fluid, okay, times the acceleration of gravity, right? Mass of the displaced fluid times the acceleration of gravity. Here you go. G here on the left side is the same G that's on the right side. But the masses are not necessarily the same, right? We do know that the mass on the left side can be written down in terms of its density, okay? And its volume. The same thing can be said about the mass of the fluid. The density of the fluid times the volume of the fluid. Okay? Now, something very important. Because the object is completely submerged, then we can state that the volume of the object must be equal to the volume of the fluid, right? The object is completely submerged. And by the way, it's not the volume of the fluid, but the volume of the displaced fluid. Let's write that down here. Not just the volume of the fluid, but the volume of the displaced fluid, right? Let's specify that here. Displaced fluid, displaced fluid, displaced fluid. And here, displaced fluid. Because of that, this inequality can be here written as rho of the displaced fluid times V. This V is equal to this V. So we can write that down, that for the object to sink, the density of the object must be greater than the density of the displaced fluid. In other words, rho divided by the other rho must be greater than 1. Make sense? Okay, very simple. Very simple derivation, right? If you know how to derive, of course, right? If you know the result, of course. Here you go, like that. This. And then we apply the same reasoning for the other situation. Okay, if this is the condition for a sinking object, let's see here. This is going to be the condition for a floating object. An object floats, end up floating if its buoyant force ends up being greater than its weight. But don't forget, when it's completely submerged, right? After the object moves upwards, okay, what's going to happen? You're going to have this net force propelling the object upwards. The object's going to acquire a velocity, and eventually it's going to float. Here you go, here you go. Oh, no. Eventually it's going to, oh, no. It's on. Okay, now it should go. Eventually it's going to float here. The final velocity is going to be 0. Okay, we can erase this arrow, this vector. Okay, the net force is going to be 0 because now the object is floating. There will be a buoyant force. The buoyant force is going to be slightly smaller because it's only a fraction of the object that's submerged. Okay, and this buoyant force the magnitude of this buoyant force is going to be equal to the magnitude of the weight of the object. Like that. Okay? The net force will be equal to 0. That's what's going to happen when the object reaches the surface. But while it is completely submerged, right? You have this net upward force. So let's going back here to this net force, and here you go. We can use the same reasoning we had before. I'm just going to, floating object. Sinking object, now floating object. The weight must be less than the buoyant force, right? All I have to do is to change this inequality sign. Oh, what's going on here? Okay, I know what I did. Good, here you go. All you have to do is to change this inequality sign. The weight of the object must be less than the weight of the displaced fluid. Okay, G cancel out with G just like before. It's just the sign here must be less. Mass can be here written in terms of the density times the volume. On the left side is the density of the object times the volume of the object. On the right side is the density of the displaced fluid times the volume of the displaced fluid. But because the object is completely submerged, it means that its volume coincides with the volume of the displaced fluid. So keep on going here. Here we go. This volume is the same as this volume. That's what I wrote here. Consequently, this volume cancels out with this other volume. And look what happens. For an object to float, its density must be smaller than the density of the fluid. Okay? Styrofoam, for instance, they have densities that are smaller than the density of the water. Let's take a look at Google, right? Styrofoam density. Let's see what's the density of styrofoam. Okay, here you go. 0.01 to 0.05 grams per cubic centimeter. It's very small, right? How many? 100 times less than the density of water. Anywhere between 10 to 50 kilograms per cubic meter, or 0.01 to 0.05 grams per cubic centimeter. Remember that the density of water is 1,000 kilograms per cubic centimeter. Okay. And now the last one, for an object to be neutrally buoyant. And neutrally buoyant means that the net force applied to the object, neutrally buoyant. Object, neutrally buoyant object, the condition must be the weight equal to the buoyant force. Here you go. Here you go. That's how you should visualize it. The buoyant force equal to the weight. Fishes have this capability, and we humans also have this capability of maintaining ourselves neutrally buoyant. Okay, so the weight must be equal to the buoyant force, equal, same derivation. Oops. Same derivation as before. It's just a different result because the condition is different. The volume of the displaced fluid must be equal to the volume of the object. And here you go. If you want to remain neutrally buoyant underwater, your density must be equal to the density of the fluid. And here you go. Those are the three interesting conditions that we have there. We humans have this ability to remain neutrally buoyant because our overall density is very close to the water density. Okay, ability is of H, right? Next time you go to the swimming pool, you go swimming, right? Mama, try the following. You know, next time you go swimming, 1, float above the water, but do that safely, right? Do that safely, of course. Of course. Float above the water and completely exhale. Okay? Completely exhale, right? What's going to happen when you exhale? You will notice that you will start to sink. That's because your overall density became less than the water density. The moment that you fill your lungs with air, your density is lower than the density of the water. If you completely exhale the air, your density becomes larger than the density of water, okay? Float above the water and completely exhale. When you exhale, you're going to notice that you will start to sink. That's because the overall density, your overall density, becomes less, becomes more, not less, than the density of water, than the water density. However, if you inhale, fill your lungs with air, right? Your overall density becomes larger than the water density, becomes not larger, it's smaller than the water density. And you will float, okay? Next time you go swimming, float above the water and do the following. Here you go, float above the water. And do the following. Do that safely, of course. First, really exhale. Empty your lungs. Empty your lungs of air. Completely exhale. When you exhale, you notice that you start to sink. That's because your overall density becomes more than the water density, than the density of the water. However, if you inhale to your lungs with air, your overall density becomes less than the water density, and you will float. Okay. So that's all you have for chapter 11. Okay. It's 12:34 right now. You have 15 more minutes to go. Okay, and then what we have to do, let's start chapter 16. Waves and sound. And also let me take attendance. Also, did I raise my hand and I didn't notice it? Let me see. How do I? Yeah, I raised my hand here. I didn't know. Lower hand. Okay, good. Any questions? This part on fluid dynamics is very kind of easy, right? Because we use very simple mathematical techniques. And now let's see. Let's take a look now at waves. Someone's trying to come in. Okay, good. Okay, let's start with waves. Okay, that there is this duality. There is this duality in physics. Physical objects, and waves. Okay. Physical objects or particles, physical objects, and the physical object can be either a point particle, or a rigid body. And waves. Physical objects have mass, whereas a wave is an abstract concept that has no mass whatsoever. It is closely related to energy. A wave is energy that propagates in a medium, okay, and has no mass because it's energy. Because it is energy, it has no mass whatsoever. It's a very important concept in physics that helps us explain a lot about the universe. Okay, it's a very powerful concept. Although extremely abstract and genetic, it's used in physics to explain many real-life phenomena. Okay, let me give you a list of the types of waves that we have out there. The most common one and easier to visualize, the most common one and easier to visualize easier to visualize is a wave that propagates along a string or a coil. When you pluck a string, you put it to oscillate. Let's put oscillate here. Consider, for instance, here you go. Consider, for instance, the strings of a guitar. Right? When you pluck the string, you put it to oscillate. Although the string is moving, we say that there is an energy propagating along this string. This is string. Let's see if I have it's always good to have an illustration for that. Let's see here. '26. Let's see this one here. Oh. Illustrations. Yeah, it's a shame I do not have here. It should be elsewhere. Let me see if I can find. It should be in a different folder of mine. Open a new window. Colleges. This one here. To the transcript lab. Let me pause the video, okay? The recording. Remind me to start recording again, okay? I'm gonna pause moment. Okay, so here you go. Let's start here. Consider a string that has both ends. That's a very long string. Consider a very long string that has both ends free. You get one of the ends and you move it up and down with your hand. Okay? What you're going to see? You're going to see something like that, you know? Here you get instant t equal to 0. Okay, I'm moving this string up and down on this end. What you're going to see? You're going to see that it is as though this string is propagating from the left to the right. Okay? We have this illusion, right? That the string is propagating, the string itself, when in reality, it's not the string that's propagating from the left to the right, when in reality, it is the energy that you are applying to the string that is propagating from the left to the right. Okay, that's what we call a train of waves. 16, 17, 18. See, I am simulating what you'd see in real life if you were to get a rope or a string and move it up and down, a very long string. It will move from the left to the right. Okay? 25, 26, and so on. Okay? So let's write that down. Close it here. This is, put it, let's move it to this spot. What time is that? 4 more minutes to go, okay? The most common type of a wave and easier to visualize is a wave that propagates along a very long string or coil. Consider, for instance, a very long string, with both of its ends loose. Okay? When you move the one end of the string or rope, right, can be a very long string, is a wave that propagates along a very long string, comma, rope or coil. When you move one end of the string up and down, comma, you will visualize something that seems to be moving from away from your hand, right? Away from your hand. Like that. Okay, I can even, we're running out of time here. Let's see. Yeah. 2 more minutes to go. And let's see what I can do in 2 minutes. Okay, moving from your hand. Do something that is moving away from your hand is not the string itself, but the energy that you produce with your upward and downward motion, okay? It's energy propagating. Another example, right, is the water waves. Water waves is another example of waves. You have the material medium, which is water, right? Which is water. Which is water. And within this medium, a disturbance or energy is transported. Okay, this energy is visualized as a wave. Okay, let's put it this way, it's better this way. Sound is another example of a wave. This type of wave propagates in any material medium, air, metals, gas, but does not propagate in vacuum. Okay, you can hear me? You can hear me and anybody else? Anybody else? Because the sound wave is moving from its source to your ear, which by the way, is a sensor of sound. It's a sensor that can detect sound. Okay. Sound. Okay, have you ever heard the word sensor? The ear is a sensor that can detect sound. So let's, it's already 12:51, right? Let's stop writing here and read a little bit about those waves. We're going to elaborate a little bit more next time. And I see you the day after tomorrow, right? And don't forget, I have office hours right now. If you want to ask, if you want to hang around and ask me some questions, I'll be available right now. Okay? See you the day after tomorrow.
Thank you, Professor.
Okay, you're welcome.
Thank you. Have a good one.
You too.